What if I told you that right now, at this very moment, somewhere beyond the asteroid belt, two frozen moons are defying everything we thought we knew about where life could exist? One shrouds alien seas beneath an atmosphere thicker than Earth's. The other erupts continuous geysers from a warm, hidden ocean. Both orbit the same magnificent ringed planet. Both contain all the essential ingredients for life. And both are so strange, so utterly unlike anything on Earth, that they challenge our very definition of a habitable world. For the next hour, you and I are going to journey 1.2 billion kilometers from home to explore Saturn's ocean worlds, Titan and Enceladus. Let me take you to places where it rains liquid methane, where ice geysers reach higher than the International Space Station, and where the search for life beyond Earth has become more than just a dream. Are you ready to witness two of the most extraordinary places in our solar system? Let's begin our journey at Saturn itself, that magnificent gas giant that has captivated humanity for centuries. Saturn orbits our Sun at an average distance of 1.4 billion kilometers, so far that sunlight takes over an hour to reach it. The planet appears as a golden jewel adorned with the most spectacular ring system in our solar system, bands of ice and rock that stretch hundreds of thousands of kilometers into space, yet remain remarkably thin. But today, we're not here for Saturn itself. We're here for two of its moons, worlds so different from each other, yet both harboring secrets that could rewrite the story of life in the universe. Can you imagine what it must be like orbiting this giant, feeling its immense gravity, witnessing its storms from space? Saturn hosts 146 known moons, a diverse family of worlds ranging from tiny irregular chunks of rock just a few kilometers across to massive spheres larger than planets. Some are captured asteroids. Others formed alongside Saturn in the ancient solar nebula. But among this multitude, two moons stand apart as the most intriguing destinations for astrobiologists and planetary scientists. Their names are Titan and Enceladus. One is enormous, cloaked in mystery beneath an impenetrable orange haze. The other is small and brilliant white, actively venting its interior to space. Both, remarkably, are ocean worlds. Both might harbor conditions suitable for life. And both were revealed in astonishing detail by one of humanity's greatest space missions. The question that drives us: could life exist in these alien environments? Between 2004 and 2017, the Cassini-Huygens mission orbited Saturn for 13 extraordinary years, fundamentally transforming our understanding of the Saturnian system. This wasn't just a flyby. This was an extended residence, a detailed investigation of an entire planetary system. The spacecraft was massive, over 6 meters tall, weighing 5,600 kilograms at launch. Powered by plutonium carrying 12 scientific instruments, Cassini represented a $326 billion investment in exploration. It was a collaboration between NASA, the European Space Agency, and the Italian Space Agency, a triumph of international cooperation. The mission made 107 flybys of Titan, 22 close approaches to Enceladus, and discovered things that seemed like science fiction. What Cassini found at these two moons changed everything. Titan and Enceladus couldn't be more different in appearance. Titan is a giant, 150 kilometers in diameter, larger than the planet Mercury, second only to Jupiter's Ganymede among solar system moons. Its mass is so great that it holds a thick atmosphere, creating the only moon with a substantial gaseous envelope. Enceladus, by contrast, is tiny, just 504 kilometers across, roughly the width of the state of Arizona. You could fit over 1,000 Enceladus moons inside a single Titan. Yet despite this dramatic size difference, both moons harbor subsurface oceans. Both show evidence of complex chemistry. Both have become prime targets in the search for extraterrestrial life. Hmm, how can two worlds so different in size share such profound similarities? We're about to find out. Let me paint you a picture of what we're dealing with. Titan orbits Saturn at a distance of 1.22 million kilometers, taking almost 16 Earth days to complete one orbit. It's cold out there. Surface temperatures hover around minus 179 degrees Celsius. Despite these frigid conditions, Titan has rivers, lakes, seas, clouds, and rain. Not water, mind you, but liquid methane and ethane. It's Earth's closest analog in the solar system, yet operates on completely alien chemistry. Enceladus orbits much closer to Saturn, just 238,000 kilometers out, whipping around every 33 hours. It's even colder at minus 198 degrees Celsius. Yet beneath its ice, an ocean warms to temperatures above freezing. Right now, as we speak, hydrothermal vents on Enceladus's seafloor are heating water, driving chemistry, possibly supporting life. Before we explore each world in detail, let's understand why these moons matter so profoundly. For centuries, humanity searched for life by looking at worlds similar to Earth, rocky planets in the habitable zone where liquid water could exist on the surface. Mars, Venus, exoplanets around distant stars. But Titan and Enceladus taught us that we were thinking too narrowly. Life doesn't need a surface ocean warmed by a nearby star. Life might thrive in hidden oceans beneath ice shells, warmed by tidal forces, protected from cosmic radiation. These ocean worlds might be far more common in the galaxy than Earth-like planets. If life exists on Enceladus or Titan, it would prove that habitable environments are abundant throughout the cosmos. The implications are staggering. We might live in a universe teeming with life, just not where we expected to find it. As we prepare to visit each moon, I want you to let go of your earthbound expectations. Forget what you think you know about where life can exist. These worlds will challenge you. Titan will show you organic chemistry so complex it rivals Earth's, yet operates at temperatures where water is harder than steel. Enceladus will demonstrate that a moon barely 500 kilometers across can remain geologically active for billions of years, erupting geysers that dwarf anything on Earth. Both moons will make you question what's possible in our universe, and both will fill you with wonder at the sheer diversity of worlds that exist beyond our blue planet. So take a deep breath, leave Earth behind for the next hour. Let's journey to Saturn. Let's explore two ocean worlds unlike anything you've ever imagined. Let's approach Titan now, drawing closer to this enigmatic world. From a distance, you notice something immediately unusual. You can't see the surface. Unlike our moon, unlike Mars, unlike most worlds in the solar system, Titan hides beneath a thick, opaque atmosphere. The color strikes you first, orange, deep and pervasive, like a cosmic tangerine glowing with an internal light. This isn't reflected sunlight you're seeing. It's atmospheric haze, a smog of organic particles manufactured by complex chemistry high above the surface. As we get closer, you begin to appreciate the atmosphere's incredible extent. It doesn't end sharply like Earth's. It fades gradually into space, extending 600 kilometers above the surface, 10 times higher than Earth's atmosphere. This is no ordinary moon. Something special. Titan's atmosphere is extraordinary for many reasons, but let's start with the most impressive. It's denser than Earth's. Stop and think about that for a moment. You're looking at a moon, a satellite of another planet, and it has a thicker atmosphere than our own world. The surface pressure on Titan reaches 147 bar 50% higher than the atmospheric pressure you're experiencing right now. If you could stand on Titan's surface, you'd feel pressure equivalent to being 15 meters underwater in Earth's oceans. Yet Titan is smaller than Earth, with gravity just 14% as strong. How does it hold on to such a massive atmosphere? The answer lies in the cold. At -79 degrees Celsius, gas molecules move sluggishly, lacking the energy to escape even from Titan's weak gravity. Cold becomes a trap, holding atmosphere close. Now let's talk about what this atmosphere contains, because here's where Titan truly becomes Earth's cousin. Titan's atmosphere is 95 to 98% nitrogen, the same gas that makes up 78% of Earth's air. We're talking about nitrogen, that stable, inert molecule that forms the backbone of breathable atmospheres. Only two worlds in our entire solar system have nitrogen-dominated atmospheres, Earth and Titan. This isn't a coincidence, it's a profound connection. When you breathe, you're inhaling mostly nitrogen. On Titan, you'd be immersed in nitrogen. The similarity is remarkable. Some scientists believe Titan's atmosphere resembles what Earth's atmosphere looked like billions of years ago, before life produced oxygen. Could Titan be showing us Earth's past? Could it be demonstrating how prebiotic chemistry proceeds on a world not yet alive? But Titan's atmosphere holds more than nitrogen. The second major component is methane, about 1.4 to 5.6% depending on altitude. And this is crucial. Methane on Titan plays the role that water vapor plays on Earth. It evaporates from lakes and seas, rises into the atmosphere, condenses into clouds, and falls as rain. Methane creates weather. Methane drives climate. And here's the fascinating part. Sunlight destroys methane. Ultraviolet radiation breaks methane molecules apart in the upper atmosphere within 10 to 100 million years. Yet Titan's atmosphere remains rich in methane. Something, somewhere, must be constantly replenishing it. Is it cryovolcanoes erupting from the surface? Outgassing from the interior through clathrate melting? Geological activity releasing trapped reserves? We don't know for certain. It remains one of Titan's great mysteries. The orange haze that gives Titan its distinctive color forms through one of nature's most elegant chemical cascades. High in the atmosphere, 700 to 1,000 kilometers up. Attack nitrogen and methane molecules, ripping them apart into reactive fragments. These fragments recombine into new molecules, acetylene, ethene, hydrogen cyanide, propane. These molecules react further, building benzene rings, creating polycyclic aromatic hydrocarbons, assembling into increasingly complex structures. Eventually, molecules grow so large, exceeding 8,000 atomic mass units, that they condense into solid particles. These are tholins, orange-brown organic aerosols that drift slowly downward through the atmosphere like snow. Over millions of years, they coat Titan's surface. This is organic chemistry on a planetary scale, manufacturing complexity from simplicity, building order from chaos. Cassini's instruments detected an astonishing molecular inventory in Titan's atmosphere. Benzene, the first aromatic compound found beyond Earth and Mars. Propene, a molecule never before seen on any world except Earth. In 2023, the James Webb Space Telescope detected the methyl radical, a highly reactive species that had been theorized but never directly observed. More than 100 different molecules have been identified, some bearing exotic names you'd need an organic chemistry degree to pronounce. This atmospheric chemistry rivals the complexity of Earth's atmosphere before the rise of oxygen. It proceeds entirely without life, driven by sunlight and planetary energy. And here's what keeps scientists awake at night. All these organic molecules eventually settle to the surface. for billions of years, Titan has been receiving a gentle rain of organic matter. What might be happening down there in the accumulating deposits? The atmosphere creates a greenhouse effect, but with a twist. Methane and hydrogen warm the surface by about 21 Kelvin through infrared absorption, trapping heat like Earth's greenhouse gases. But simultaneously, the thick haze layer reflects incoming sunlight back to space, creating an anti-greenhouse cooling effect of about 9 Kelvin. The net result, a warming of 12 Kelvin. Without this atmospheric blanket, Titan would be even more inhospitable than it already is. The atmosphere also shields the surface from cosmic rays and energetic particles from Saturn's magnetosphere. It moderates temperature extremes. It enables the methane cycle. In every way, Titan's atmosphere makes the surface a less extreme environment than it would otherwise be. And beneath this atmospheric shield, hidden from view, lies a landscape unlike anything else in the solar system. But we'll need to descend through the haze to see it. One more remarkable feature of Titan's atmosphere deserves mention. It exhibits what scientists call a gyroscopic wobble. The atmosphere tilts relative to the solid body beneath it, with the tilt varying over Titan's 30-year seasonal cycle while the orientation remains fixed in space. This is bizarre behavior, suggesting something dramatic happened in Titan's past. Perhaps a massive impact that tilted the atmosphere and whose effects still echo through atmospheric dynamics billions of years later. Titan continues surprising us. Every new observation raises new questions, and as we prepare to descend through this orange veil to explore the surface below, remember, you're about to see landscapes shaped by weather, by rain, by erosion, processes familiar from Earth but operating with completely alien materials. Liquid methane instead of water, organic sand instead of silica, ice, bedrock instead of stone. Are you ready to see something truly extraordinary? Imagine rain falling from alien clouds. Not water, but liquid methane plummeting toward a surface where temperatures would freeze water solid as rock. This is Titan's weather. The only other hydrological cycle in our solar system besides Earth's. But whereas Earth's water cycle operates between 0 and 100 degrees Celsius, Titan's methane cycle operates around minus 179 degrees. The principles remain the same: evaporation, condensation, precipitation, collection. Methane evaporates from lakes and seas, rises through the cold atmosphere, condenses into clouds when temperatures drop, and falls as rain. The rain collects in rivers, flows across the landscape, and pools in lakes and seas. It's Earth's water cycle in a mirror universe, executed with a different chemical at utterly alien temperatures. And like Earth's water cycle, it shapes the entire landscape. We see its effects everywhere. Titan experiences seasons just like Earth does, but on a far grander timescale. Saturn takes 2945 Earth years to orbit the Sun, and Saturn's axis tilts 27 degrees relative to its orbit, similar to Earth's 23.5-degree tilt. This means Titan goes through seasonal cycles lasting more than 7 Earth years each. Spring, summer, autumn, winter, each season persists longer than most human careers. Right now, as I speak to you, Titan is experiencing northern summer. The North Pole basks in continuous sunlight for years on end, warming the methane lakes and seas, increasing evaporation, driving atmospheric circulation. In 7 years, autumn will arrive. In 15 years, winter will grip the northern hemisphere. The lakes will cool. The methane cycle will shift. And we'll be watching from Earth, tracking the changes across this vast seasonal progression. Rain on Titan is rare but spectacular. During Cassini's 13-year mission, scientists documented methane rainfall only a handful of times, but when it occurs, it's dramatic. On September 27, 2010, an enormous arrow-shaped storm appeared at Titan's equator. The storm dumped methane rain across a 500,000 square kilometer region, subsequently darkening the Belay dune field as liquids soaked into the surface. Precipitation intensities can exceed 30 centimeters per day, comparable to Hurricane Harvey's catastrophic rainfall in Houston. But here's what makes Titan's rain truly alien: the raindrops themselves. Due to low gravity and thick atmosphere, methane raindrops grow much larger than Earth's water drops, up to 1 centimeter in diameter, nearly twice the size of our largest raindrops. Yet they fall gently, drifting down at just 1.6 meters per second, like snowflakes on Earth. Clouds on Titan form through mechanisms both familiar and strange. Tropospheric methane clouds hover at 15 to 18 kilometers altitude at lower latitudes, forming and dissipating as convection carries moist air upward. These clouds resemble Earth's cumulus formations. But above 60 degrees latitude, permanent ethane clouds blanket the regions year-round, a phenomenon with no Earth analog. These clouds never dissipate. They simply persist, stable and unchanging. In 2023, the James Webb Space Telescope observed convective clouds in the northern hemisphere over several days, watching them grow and evolve. The clouds rise to higher altitudes as strong convection lifts them. They drift with upper-level winds. They rain out their methane, then dissipate. Its weather, recognizable yet utterly alien, wind shapes Titan's climate as profoundly as precipitation. At 30 degrees latitude, winds scream through the mid-latitudes at 200 meters per second, over 700 kilometers per hour, faster than the strongest hurricanes on Earth. These super-rotating winds circle the globe far faster than Titan's rotation, driven by the differential heating between equator and poles. An intertropical convergence zone migrates pole to pole with the seasons, unlike Earth's ocean-constrained ITCZ. Following the northern spring equinox in August 2009, Cassini observed rapid atmospheric reorganization. The South Pole developed a massive vortex featuring extreme trace gas concentrations and hot stratopause temperatures. The atmosphere was literally reconfiguring itself in response to changing sunlight. Titan's atmosphere is alive, dynamic, constantly reshaping itself through processes we're only beginning to understand. Surface humidity on Titan reaches about 60% at locations where we have measurements, surprisingly similar to many places on Earth. The air feels saturated with methane vapor near the surface, gradually drying at higher altitudes. This humidity feeds the clouds, drives the precipitation, maintains the cycle. But here's the puzzle that keeps scientists debating. Where does the atmospheric methane ultimately come from? The methane cycle can only redistribute methane that already exists in the atmosphere. It can't create new methane. Yet methane is constantly being destroyed by sunlight. Calculations show that without replenishment, Titan's atmosphere would lose its methane within 10 to 100 million years, a geological eye blink. Something must be feeding methane into the atmosphere from some deeper reservoir. Is it outgassing from the interior? Geovolcanism? Clathrate melting? Whatever the source, it's been operating for billions of years. The methane cycle operates continuously, but not uniformly. Seasonal variations create dramatic differences in activity between hemispheres. During northern summer, evaporation from the northern lakes intensifies, increasing atmospheric methane concentrations in the northern hemisphere. Clouds become more frequent and vigorous. Rainfall events increase. The whole system accelerates. Then, as autumn approaches and winter arrives, the process reverses. The northern hemisphere cools. Evaporation slows. Atmospheric circulation shifts southward. The cycle continues, but its intensity and location migrate with the seasons. This is planetary scale climate, driven by the same orbital mechanics that give Earth its seasons, but expressed through methane instead of water. And just like Earth's climate shapes our landscape through erosion and deposition, Titan's methane cycle sculpts its surface. Let's descend now and see what it has created. We're descending through Titan's thick atmosphere now. And as the orange haze begins to clear, you start to see surface features. The view is dim. Only 0.1% of Earth's surface illumination reaches the ground here. Everything has an orange cast, like perpetual twilight at dusk. And there, spread across the northern polar region, you see something that makes your breath catch. Bodies of liquid. Lakes. Actual standing liquids on another world's surface. These aren't water. They're liquid hydrocarbons, methane and ethane, pooled in depressions carved from water ice bedrock. But they're real. They have waves. Some are larger than Earth's Great Lakes. For the first time since leaving Earth, you're looking at another world with liquid on its surface. How does that make you feel? What does it mean to know that out here, 1.2 billion kilometers from home, liquid laps against alien shores? Let's explore the largest of these liquid bodies, Krakenmeer. This immense sea spans approximately 500,000 square kilometers, larger than the Caspian Sea, roughly the size of all 5 Great Lakes combined. Think about that scale. This isn't a pond or a puddle. This is a sea of liquid methane and ethane that could swallow California. Radar measurements reveal depths exceeding 300 meters in places, with seafloors detected at 170 meters along certain transects. Small waves ripple across its surface, just 1.5 centimeters high, with velocities of 0.7 meters per second, driven by gentle winds. Tidal forces from Saturn create amplitude variations of 1 to 5 meters, though these tides move slowly in the thick atmosphere. Right now, as we look down at Krakenmeer, its surface is moving, flexing, responding to Saturn's gravity a million kilometers away. It's alive, dynamic, an ocean that breathes with the rhythms of planetary forces. Ligea Mare, the second largest sea, reveals different characteristics. Spanning 126,000 square kilometers, it contains remarkably pure liquid methane with dissolved nitrogen. The transparency is extraordinary. Radar measurements show a loss tangent of just 4 times 10 to the negative 5th, meaning radio waves penetrate deeply with minimal absorption. You could see to depths of 200 meters if you could somehow swim in this minus 179-degree liquid. The shoreline extends more than 2,000 kilometers and displays fascinating variety. The eastern and southern margins show crenulated, hummocky terrain, heavily eroded coastlines battered by waves and weather. The western and northern shores appear subdued and smooth flooded river valleys, creating rear coastlines where rivers once carved channels that were subsequently drowned as lake levels rose. Each shoreline tells a geological story of changing climate and shifting liquid levels over millions of years. In 2014, Cassini radar spotted something strange in Ligea Mare, a bright feature that appeared, disappeared, and reappeared over subsequent observations. Scientists dubbed it the Magic Island. Spanning 260 square kilometers, it remained visible for weeks before vanishing. What could cause a transient bright feature in a liquid hydrocarbon sea? Several hypotheses compete: nitrogen bubbles rising from the depths, released by warming or pressure changes, wind-driven surface waves creating temporary rough patches that reflect radar differently, subsurface movement of solids, perhaps organic icebergs floating then sinking, or even geological activity releasing material from below. We don't know which explanation is correct. The magic island represents one of Titan's many enigmas, a phenomenon we've observed but don't yet understand. It reminds us how much remains mysterious about these alien seas. Travel to the southern hemisphere and you'll find Ontario Lacus, Titan's only major liquid body south of the equator. This lake is peculiar, extremely shallow, averaging just 0.4 to 3.2 meters deep. That's puddle depth compared to the northern seas. The surface is mirror smooth, varying less than 3 millimeters over 100-meter spans, smoother than the calmest lake on Earth. It resembles a terrestrial mudflat more than a sea, perhaps a remnant of a once larger body that has evaporated during southern winter. Why does the southern hemisphere have so few lakes while the northern hemisphere has hundreds? The answer lies in Saturn's eccentric orbit. Southern summers occur when Saturn is closer to the Sun, making them shorter but more intense. This increased heating evaporates southern lakes more efficiently. Northern summers are longer but cooler, allowing liquids to persist. Climate on Titan operates through orbital mechanics we're only beginning to understand. The Northern Lake District concentrates 97% of Titan's hydrocarbon lakes within a 900 by 1,800-kilometer region. Hundreds of smaller lakes dot the terrain alongside the major seas. Some show sharp-rimmed morphology suggesting explosive formation, Mar-like craters created when liquid dissolved underlying ice and released nitrogen gas explosively. Others display classic karst features where liquid hydrocarbons dissolved soluble surface ice, creating sinkholes that subsequently filled with liquid. The variety of formation mechanisms reveals active processes, dissolution, explosive degassing, tectonic fracturing, erosion. These aren't ancient relics. These are geologically young features shaped by ongoing processes. Collectively, these lakes and seas contain 300 times Earth's proven oil reserves and hundreds of times more natural gas and liquid hydrocarbons than all known reserves on our planet. Titan is a world drowning in energy resources that would be impossible to exploit, but staggering to contemplate. Standing at the shore of a Titan lake, what would you experience? The liquid laps gently against ice boulders, each wave tiny and slow in the thick atmosphere. The liquid is transparent. You can see into its methane-ethane depths where organic sediments accumulate on the bottom. The atmosphere presses heavily around you. Above, orange haze obscures the stars. The temperature would kill you instantly, minus 179 Celsius. The atmosphere lacks oxygen, you couldn't breathe. The pressure would feel strangely normal, like being underwater, but the air is poison. Yet despite the hostility, there's beauty here. Liquid moves. Weather happens. Erosion shapes shores. This is a world that operates, functions, evolves. And hidden beneath these alien seas and beneath the ice bedrock below, Titan conceals its greatest secret, a deep ocean of liquid water. Travel away from Titan's polar lakes toward the equator, and the landscape transforms dramatically. The lakes vanish. The terrain darkens. And stretching across the equatorial regions, you encounter one of Titan's most spectacular features, vast dune fields covering 14.6 million square kilometers, 1.5 times the area of Earth's Sahara Desert. But these aren't dunes of silicate sand like the Sahara or the Arabian deserts. These dunes consist of something far more exotic, solid hydrocarbons, organic particles manufactured in the atmosphere and precipitated as brown-orange tholins. Imagine deserts made of the building blocks of life, sand composed of complex organic molecules, dunes assembled from the same carbon-based chemistry that could lead to biology. You're looking at prebiotic chemistry on a planetary scale, accumulated grain by grain over billions of years into massive sand seas. What secrets do these organic dunes hold? These dunes are enormous. Individual dunes tower 80 to 130 meters high, comparable to Egypt's Great Pyramid. They stretch over 100 kilometers long, maintaining remarkably straight courses across the landscape. They space themselves 1 to 4 kilometers apart in patterns so regular they look artificial, though they're entirely natural features created by wind and sand transport. The dunes are linear, meaning they form long, straight ridges parallel to the prevailing wind direction. But here's where it gets interesting. The dunes propagate eastward, yet the surface winds blow westward. Seems impossible. How can dunes move upwind? The answer reveals Titan's subtle complexity. Rare methane storms occurring roughly every 15 years generate powerful high-altitude gusts that dominate sand transport despite their infrequency. Between storms, normal westward winds are too weak to move the grains. The storm winds drive everything east. The dunes remember these rare but powerful events. What are these dunes made of? Laboratory analysis and spectroscopic observations suggest a complex mixture. The grains form through cosmic ray bombardment of acetylene ice in Titan's atmosphere, synthesizing aromatic hydrocarbons including benzene, naphthalene, and phenanthrene. These molecules condense into solid particles roughly 0.4 inches in size, similar to medium sand on Earth. The material is dark brown to orange-brown, rich in carbon and nitrogen. It's not quite like anything on Earth. It's organic sediment, but not biological. It formed through chemistry, not life. Each grain represents the endpoint of an atmospheric chemical cascade that began with methane and nitrogen molecules high above, subjected to radiation, assembled through countless reactions, grown in complexity, and finally settled as solid matter. The dunes are literally made of atmosphere that fell from the sky and accumulated into mountains. Now shift your view away from the dark dune fields toward one of Titan's brightest regions, Xanadu. This is a continent-sized bright feature, approximately the size of Australia, centered near Titan's equator. Xanadu represents Titan's most rugged, mountainous terrain. Mountain chains rise to 3.3 kilometers. Elevation at Mithra Montes with peaks commonly exceeding 2,000 meters and slopes steeper than 30 degrees. This is challenging terrain. If you could somehow walk here, you'd need mountaineering equipment. The landscape consists of water ice, as hard as concrete at these temperatures, carved by methane erosion into hills, valleys, and canyons. Extensive river networks drain through integrated channel systems that would look familiar to any geologist, except these rivers carry liquid methane instead of water and cut through ice instead of rock. Xanadu is ancient, heavily impacted, eroded, a window into Titan's deep geological history. Impact craters mark Xanadu at twice the density found elsewhere on Titan, suggesting either greater age or different resurfacing rates. Yet even here, craters are remarkably rare. Only 49 to 61 potential impact structures have been identified across Titan's entire surface. For a 4.5 billion-year-old world, that's extraordinarily few. Where did all the craters go? Titan's thick atmosphere pulverizes small impactors before they reach the surface. Objects smaller than about 15 kilometers across disintegrate during atmospheric entry. But the atmosphere can't protect against large impacts. So why are craters rare? Active erosion provides the answer. Methane rainfall erodes exposed crater rims. Wind-blown organic particles bury crater floors. Cryovolcanic flows may have resurfaced regions. And in lowland areas, sediments accumulate in what some scientists call cosmic swamps, perpetually damp organic mud that gradually fills topographic lows, erasing ancient structures. One crater holds special significance, Selk Crater, 90 kilometers in diameter, its floor completely covered in organic sediments preserved undisturbed. No rain has disturbed this region. It lies in an equatorial rain shadow. The organics that accumulated here settled directly from the atmosphere and from the impact ejector itself. When the impact occurred, it melted surface ice, creating a brief pool of liquid water that interacted with surrounding organics before freezing again. That mixture, water, organics, energy from impact, created conditions favorable for prebiotic chemistry. Now, 80 million years later, the products of that chemistry lie frozen and preserved. NASA selected Selk as the target for its Dragonfly mission precisely because it offers pristine samples of both atmospheric organics and impact-generated chemistry. In 2034, an 8-rotor drone will land here and analyze what it finds. We wait eagerly for what Selk will teach us. Across Titan's surface, you see evidence of processes both familiar and alien. Rivers carved into ice bedrock by methane flow, coastlines shaped by waves and tides, mountains uplifted by internal forces, dunes built grain by wind, craters gradually erased by erosion and burial. Every process we see on Earth has an analog here. Tectonics, volcanism, erosion, deposition, weathering, mass wasting. The inventory of geological processes is nearly identical, but the materials are different. The temperatures are different. The chemistry is different. Titan is Earth's cousin twice removed, recognizable in outline, but alien in detail. And everything you're seeing, every landscape feature, every geological process, occurs above a deep secret. Beneath the ice bedrock hidden from view lies an ocean of liquid water, an ocean that might, just might, harbor life of its own. It's time we talked about Titan's hidden depths. Everything we've explored so far, the atmosphere, the methane cycle, the lakes and seas, the organic dunes, all of this exists at Titan's surface or above. But Titan conceals a deeper mystery. Roughly 55 to 80 kilometers beneath the ice bedrock you've been looking at, beneath the solid water ice that forms Titan's outer shell, there exists a layer of liquid water. An ocean that has persisted for billions of years, warmed by radioactive decay in Titan's core and by tidal flexing from Saturn's gravity. We can't see this ocean directly. We can't sample it remotely. But Cassini proved it exists through multiple independent lines of evidence. And now we must ask, what conditions prevail in this hidden ocean? Could it support life? Could water-based organisms live in Titan's depths while methane-based chemistry proceeds on the surface above? Titan might harbor two completely separate habitable environments. How do we know the ocean exists? The first clue came from radio signals sent by the Huygens probe during its descent in January 2005. The propagation characteristics suggested atmospheric properties consistent with a decoupled interior structure. But stronger evidence came from Cassini's gravity measurements and direct observations of surface changes. During Cassini's flybys, precise radio tracking detected variations in Titan's gravitational field as the spacecraft sped past. The pattern of variations revealed how mass is distributed inside Titan. Models matching the observations required a liquid water layer between ice shell and rocky core. Without liquid, the gravity signatures couldn't be explained. The data left no room for doubt. Titan has a subsurface ocean. The question wasn't whether an ocean exists, but how deep, how thick, and what properties it has. Each new analysis refined our understanding. The most dramatic proof came from watching Titan's surface move. Between October 2005 and May 2007, Cassini repeatedly imaged the same surface features. When scientists compared these images, they discovered something astonishing. Landmarks had shifted position by up to 30 kilometers. The entire ice shell was sliding around, rotating slightly faster or slower than the interior. This can only happen if the outer shell floats freely on a lubricating layer, a liquid layer that decouples surface from interior. It's like Earth's tectonic plates sliding on the asthenosphere, except this is an entire planetary shell sliding on a global ocean. The surface movement directly proves the ocean's existence and demonstrates that it's global, not just a regional sea beneath one hemisphere. Titan's ice shell drifts across the ocean beneath like a ship across water, constantly adjusting, sliding, rotating over geological timescales. Titan's ocean reaches approximately 250 kilometers deep beneath an ice shell roughly 50 kilometers thick at most locations. That's an ocean deeper than Earth's 11-kilometer deep Mariana Trench, containing vastly more water than all of Earth's oceans combined, despite Titan being much smaller than Earth. The ocean consists of liquid water mixed with ammonia, which acts as antifreeze, keeping the water liquid at temperatures where pure water would freeze. Ammonia concentrations might reach 5 to 15%, lowering the freezing point significantly. The ocean's temperature probably ranges from the freezing point of the ammonia water mixture, perhaps 270 Kelvin, up to the base of the ice shell. It's a cold ocean by Earth standards, but liquid nonetheless. And unlike surface methane seas that lie fully exposed, this ocean remains protected beneath kilometers of ice, shielded from space radiation, insulated from the frigid surface temperatures. But here's the challenge. Titan's ocean lies far beneath the surface, separated from the atmosphere by 50 kilometers of solid ice. How could material exchange occur between surface and ocean? How could organic molecules manufactured in the atmosphere reach the liquid water where they might engage in prebiotic chemistry? Several pathways could facilitate transport. Impact events would be most dramatic. Large asteroid or comet impacts would punch through the ice shell, creating transient melt pools where surface organics mix with liquid water for thousands of years before refreezing. Cryovolcanism provides another route: water. Ammonia mixtures erupting from the ocean through cracks in the ice shell, flowing across the surface, interacting with organics before freezing or evaporating. Both processes have likely occurred throughout Titan's history, intermittently connecting the isolated environments of surface atmosphere and subsurface ocean. Deep within the ocean, conditions might be surprisingly favorable for life. Recent research in April 2025 tempered expectations. The ocean's depth and separation from the rocky core by high-pressure ice layers severely limits nutrient availability. If life exists in Titan's ocean, biomass might total only a few pounds planet-wide. That's minimal. A few pounds of cells distributed through an ocean larger than Earth's Atlantic. Yet the possibility remains. It contains ammonia, providing antifreeze and chemical versatility. Tidal heating from Saturn might generate currents and mixing. And over 4.5 billion years, even minimal nutrient transport could have allowed chemistry to explore countless pathways. We simply don't know whether that exploration led to life. Titan's ocean remains one of the solar system's great unknowns. A hidden sea we can measure but not observe, detect but not sample, prove exists but not investigate directly. Not yet. So Titan presents us with a profound question. Is it one world or two? At the surface, a methane-based chemical system operates in the cold, manufacturing organic complexity, cycling liquids, building molecular complexity that could potentially lead to methane-based life, a form of life we can barely imagine. Deep below, a water-based ocean persists, potentially harboring water-based life more similar to Earth's organisms yet isolated by kilometers of ice. Could both environments host life simultaneously? Could Titan be home to two independent biospheres operating on different chemistries, ignorant of each other, separated by impenetrable barriers of ice? Or is Titan a sterile world despite its habitability? A place with all the ingredients but missing some crucial spark? These questions drive our continued fascination with Titan, and they're why we're sending Dragonfly to explore in the next decade. But now, let's turn our attention to a very different world, Enceladus. We're leaving Titan now, that mysterious orange world with its hidden ocean and alien chemistry. Our next destination orbits much closer to Saturn, a moon so small you could drive across it in a day, yet so active it has revolutionized our understanding of where life might exist. Look ahead and you see it, a brilliant white star that resolves as we approach into a perfect sphere of pristine ice. This is Enceladus, barely 504 kilometers in diameter, smaller than many asteroids, yet reflecting nearly 100% of incoming sunlight. It's the brightest object in the solar system, appearing like a cosmic beacon against the darkness of space. And as we draw closer still, you notice something extraordinary at its south pole: plumes. Enormous fans of water and ice erupting continuously into space, reaching hundreds of kilometers high, sparkling in sunlight. Enceladus is alive. It's erupting. And what it's erupting could contain the answer to one of humanity's oldest questions. Enceladus orbits Saturn every 32.9 hours at a distance of 238,000 kilometers, close enough to experience enormous tidal forces from Saturn's massive gravity. The moon is tiny compared to Titan. At 504 kilometers across, it's roughly the width of Arizona. You could fit more than 1,000 Enceladus moons inside a single Titan. Its mass is equally minimal, 1.08 times 10 to the 20th kilograms, roughly 1,000th of Titan's mass. Surface gravity registers just 111 meters per second squared, about 1% of Earth's gravity. You could jump tens of meters high here without effort. Escape velocity is so low that material ejected from the surface easily reaches space. This low gravity turns out to be crucial. It allows the geysers to operate, allows material to escape, allows us to sample Enceladus's interior without landing. Sometimes being small offers advantages. Surface features on Enceladus tell a story of contrasting ages and processes. The northern hemisphere and much of the equatorial region show heavily cratered terrain, ancient surfaces dating back billions of years, scarred by countless impacts, cold and geologically dead. The ice appears weathered, slightly yellowed or grayed by eons of radiation bombardment and micrometeorite impacts. But travel toward the South Pole and everything changes. The cratering abruptly vanishes. The surface appears fresh, pristine, blindingly white. This is young terrain, possibly only thousands to millions of years old, depending on crater flux estimates. Tectonic features dominate: ridges, folds, fractures cutting through the ice. And most dramatically, 4 enormous parallel fractures slash across the South Polar region. These are the tiger stripes. These are the sources of the plumes. These are the pathways to Enceladus's ocean. And they're about to change everything we thought we knew about habitability. Now position yourself above the South Polar region and look down. 4 parallel dark lines cut across the bright ice terrain like claw marks: Alexandria sulcus, Baghdad sulcus, Cairo sulcus, and Damascus sulcus. Scientists call them the tiger stripes. Each extends roughly 130 kilometers long and 2 kilometers wide, massive fractures that penetrate deep into Enceladus's ice shell. The fractures don't appear random. They space themselves remarkably evenly at 35-kilometer intervals, as regular as ripples on water. Each stripe shows similar morphology, a central fracture plunging 500 meters deep, flanked by ridges 100 meters tall, spaced 2 to 4 kilometers apart. The stripes appear darker than surrounding terrain because they're dusted with material from the plumes, organic particles, salts, ice grains coating the fracture walls. And these fractures are warm. Incredibly, impossibly warm for a moon this small, this far from the sun. Something is heating them from below. Thermal measurements reveal the astonishing truth. Damascus sulcus reaches temperatures up to 190 Kelvin, that's minus 83 Celsius, which sounds cold until you realize the surrounding terrain sits at 75 Kelvin, minus 198 Celsius. The tiger stripes are more than 100 degrees warmer than their surroundings. Cassini's infrared spectrometer measured 5.8 gigawatts of thermal radiation from the South Polar region during close flybys, with revised estimates suggesting 15.8 gigawatts total heat output. That's equivalent to 20 coal-fired power plants continuously operating. It's 2.6 times the thermal output of Yellowstone's geothermal features. For a moon barely 500 kilometers across, this heat output defies expectations. Something extraordinary is happening here. Enormous amounts of energy are flowing from Enceladus's interior to its surface through these 4 narrow channels. The tiger stripes are thermal pipelines from an active ocean world. But heat isn't the only thing emerging from the tiger stripes. Material erupts continuously. Water, ice, salts, organics, all blasting into space at 800 miles per hour. Over 100 individual geysers have been identified through careful imaging, each one a distinct jet of material launching from specific locations along the fracture walls. The jets combine into massive plumes visible from thousands of kilometers away. Some material reaches velocities of 3.4 kilometers per second, fast enough that particles escape Enceladus entirely and feed Saturn's E-ring, a tenuous dust ring extending from Mimas's orbit beyond Titan. Approximately 200 kilograms per second vents continuously. Not a violent explosion, but a steady, persistent outpouring of material from the ocean below. Most erupted material eventually falls back to Enceladus as snow, keeping the South Polar region young and fresh, constantly resurfacing itself through its own eruptions. The geysers never stop. They're operating right now as we speak. What powers these eruptions? What keeps Enceladus active when it should have frozen solid billions of years ago? The answer lies in orbital resonance and tidal heating. Enceladus orbits Saturn in a 2001 resonance with the larger moon. Dione. Enceladus completes exactly 2 orbits for every 1 orbit of Dione. This resonance maintains Enceladus's orbital eccentricity at 0047, keeping the orbit slightly elliptical rather than circular. As Enceladus travels this elliptical path, its distance from Saturn varies by about 9% through each orbit. Saturn's immense gravity creates tidal bulges that strengthen and weaken with varying distance. This continuous squeezing and stretching generates friction throughout Enceladus's interior, producing up to 50 gigawatts of heat, 200 times more than radioactive decay alone could generate. Without this tidal heating, Enceladus would be dead. Instead, it's one of the most geologically active bodies in the solar system. Size doesn't determine destiny. Orbital mechanics does. Let's descend now toward the tiger stripes themselves and examine them more closely. From orbit, they appeared as simple dark lines. But as we approach, their true character reveals itself. These are massive geological features, fractures that dwarf the Grand Canyon in depth and extend for hundreds of kilometers. The walls rise and fall in rhythmic ridges like frozen waves. The central trenches plunge half a kilometer into Enceladus's ice shell. And along these fracture walls, geysers erupt continuously, some as focused jets, others as diffuse curtains of material. The tiger stripes aren't static features carved long ago and now dormant. They're active faults, continuously opening and closing, breathing with the rhythm of tidal forces. They flex and pulse with every orbit around Saturn. And this tidal breathing controls the intensity of the eruptions, turning the plumes up and down like adjusting a faucet. The fractures are alive in a geological sense. Carolyn Porco's imaging team identified the tiger stripe's nature through systematic observations over many orbits. Each flyby provided new data, different lighting angles, varied perspectives. The breakthrough came when they positioned Cassini with the sun behind Enceladus, creating backlit conditions where the plumes became spectacularly visible. Suddenly, what had been hinted at in earlier images became undeniable. Enceladus was erupting. The images from November 2005 showing the plumes in full glory made headlines worldwide. This wasn't just a frozen ice ball. This was an active world venting its interior to space. The discovery transformed Enceladus from a curiosity into a primary astrobiology target. Porco described the moment of seeing the first clear plume images as one of the highlights of her career. Sometimes, a single image changes everything. Those images changed how we think about habitability in the outer solar system. Observations over multiple orbits revealed something fascinating. Plume intensity varies by a factor of 4 through Enceladus's orbit around Saturn. When Enceladus reaches apoapsis, its farthest distance from Saturn, tidal forces decrease and the tiger stripes experience tension, pulling them open wider. Water and ice vent more vigorously during these periods. Plumes reach maximum intensity. Then, as Enceladus swings toward periapsis, closest approach to Saturn, tidal forces increase, compressing the tiger stripes and partially closing the fractures. Flow decreases. Plumes diminish. This tidal breathing happens every 33 hours as Enceladus completes its rapid orbit. The fractures open and close. The geysers surge and ebb. The moon literally breathes with the rhythm of its dance around Saturn. This variability proved that the tiger stripes penetrate deeply into Enceladus, connecting directly to reservoirs of liquid water that respond to tidal forces in real time. But how did the tiger stripes form in the first place? Why 4 parallel fractures at regular spacing? Doug Hemingway's 2019 analysis provided elegant answers. Baghdad's sulcus formed first, cracking open where the ice shell is thinnest at the South Pole and where tidal stresses reach maximum values. As material erupted from Baghdad, it snowed back down onto the surrounding terrain, accumulating as deposits on the flanks. This added weight loaded the ice shell, flexing it downward. At a distance of 35 kilometers from the original fracture, stress concentrations reached critical values, and a second fracture opened parallel to the first. The process repeated. Cairo formed, then Alexandria, then Damascus. Each new fracture relieved stress but created new loading patterns that eventually triggered the next crack. The tiger stripes are self-organizing features, their regular spacing determined by mechanical properties of ice and the geometry of loading. They're a natural consequence of eruption and accumulation cycles. The tiger stripes concentrate carbon dioxide ice and simple organic compounds, materials found nowhere else on Enceladus's surface. This unique composition directly reflects ocean chemistry. The CO2 and organics originate in the subsurface ocean, travel up through the fractures mixed with water, and deposit on the fracture walls and surrounding terrain as the plumes fall back. Every grain of material coating the tiger stripes spent time in Enceladus's ocean. Every particle of ice in the plumes samples subsurface water from just hours or days ago. The tiger stripes aren't just fractures, they're sampling conduits providing direct access to an extraterrestrial ocean. Nothing else in the solar system offers this convenience. Europa, Ganymede, Callisto, and Titan all have subsurface oceans, but they're sealed beneath kilometers of solid ice. Only Enceladus vents its ocean to space where we can analyze it. This accessibility makes Enceladus extraordinarily valuable for astrobiology. Temperature measurements along the taiga stripes show remarkable variability. Some locations are extremely warm by Enceladus standards, 190 Kelvin. Others are cooler. The hottest regions correspond to the most active geysers, suggesting direct correlation between heat flow and eruption activity. These warm zones likely overlie areas where the ice shell is thinnest, where fractures penetrate deepest, where connection to the underlying ocean is most direct. Think of the taiga stripes as thermal and material pipelines between ocean and space. The heat you're measuring? That's geothermal energy from hydrothermal vents on Enceladus's seafloor. The warmth you're detecting? That's the ocean's warmth, conducted through ice and carried by escaping water. The temperature tells you that somewhere below, liquid water exists at temperatures well above freezing. The tiger stripes are Enceladus's way of telling us, I'm warm. I'm active. I have liquid water. Explore. Cassini made 22 close flybys of Enceladus between 2005 and 2015, with the closest passes diving to altitudes of just 49 to 52 kilometers above the surface, low enough to fly directly through the plumes. Each flyby provided unique data. The July 14, 2005 flyby first confirmed plume composition. The March 12, 2008 flyby at 52 kilometers altitude provided the most detailed plume chemistry measurements. The October 28, 2015 flyby detected hydrogen. Each encounter refined our understanding. By mission's end, Enceladus had transformed from a small icy moon thought to be geologically dead into the solar system's most promising location for finding life beyond Earth. 22 flybys. "22 opportunities to sample an alien ocean. 22 chances to search for biosignatures. And what those flybys discovered exceeded anyone's expectations. Let me tell you about the ocean those plumes revealed. Now we must address the central question. Does Enceladus merely have a regional reservoir of liquid water beneath the South Pole, or does a global ocean exist beneath the entire ice shell? This distinction matters profoundly. A regional sea might be a transient feature, warmed temporarily by tidal friction but destined to freeze. A global ocean suggests long-term stability, sustained habitability, and conditions favorable for life over billions of years. Multiple lines of evidence from Cassini's gravity measurements and libration studies converged on a surprising conclusion. Enceladus harbors a global ocean. The entire ice shell all around the moon floats atop liquid water. Enceladus isn't just an active ice world with localized water. It's an ocean world, an aquatic planet encased in ice. And that changes everything. Luciano East led the gravity measurements that revealed the ocean's presence. During close flybys, Cassini's radio signal provided a precise measure of the spacecraft's velocity as Saturn's and Enceladus's gravity tugged on it. By tracking tiny variations and Doppler shift changes in radio frequency caused by spacecraft acceleration, scientists could map Enceladus's internal density distribution. If Enceladus consisted of solid ice all the way through with a rocky core, the gravity signatures would follow a specific pattern. But the measured gravity didn't match that pattern. Instead, it revealed lower density beneath the South Polar region, consistent with liquid water. More importantly, the gravity measurements showed that this low-density layer extended beyond the South Pole, suggesting a global rather than regional water layer. The ocean announced its presence through its gravitational fingerprint. Independent confirmation came from libration measurements, detecting Enceladus's wobble as it orbits Saturn. If the ice shell and rocky core are rigidly connected, the Moon wobbles by a predictable small amount. But if a liquid layer separates shell from core, allowing them to move independently, the wobble amplitude increases dramatically. Thomas and colleagues measured Enceladus's libration at 0-20 degrees plus or minus 0-14 degrees, significantly larger than possible for a rigid body. This proved the ice shell slides freely atop liquid water. And because libration is measured by tracking surface features as Enceladus orbits, the measurement samples the entire Moon, not just the South Pole. The enhanced libration works only if water exists globally. Two independent measurement techniques, gravity and libration, both concluded global ocean. The evidence became overwhelming. The ice shell averages 19 to 25 kilometers thick globally, but dramatically thins at the South Pole to perhaps 1 to 5 kilometers where the tiger stripes penetrate through. This thin region allows direct connection between ocean and space, explaining why plumes erupt from the South Pole specifically. The ocean beneath reaches approximately 10 kilometers deep at the South Pole, with models suggesting a global ocean 26 to 31 kilometers deep, deeper than Earth's deepest ocean trenches, deeper than Mount Everest is tall. For comparison, Enceladus's ocean contains about 2% of Earth's total ocean volume, despite the Moon being only 1/7 the diameter of Earth's moon. It's a substantial body of water by any measure. And unlike surface oceans exposed to space and radiation, Enceladus's ocean remains protected beneath its ice shell, insulated, shielded, maintained at temperatures and pressures conducive to chemistry and potentially to life. What are conditions like in this ocean? Temperature remains above 273 Kelvin 0 Celsius to prevent freezing, but how much warmer depends on location and depth. Near the ice shell ceiling, temperatures probably hover just above freezing. But at the ocean floor where hydrothermal vents operate, temperatures reach 90 Celsius or higher, possibly 150 to 80 Celsius at the vent mouths themselves. The ocean is salty. Chloride concentrations reach levels slightly below Earth's seawater, making it a brine rather than pure water. pH measurements from plume chemistry indicate alkaline conditions with pH 8.5 to 10.5, enriched in bicarbonates and carbonates. This alkaline chemistry closely resembles Earth's lost city hydrothermal field in the mid-Atlantic ridge, an environment where terrestrial life thrives without sunlight, deriving energy from chemical reactions between water and rock. Enceladus's ocean chemistry mirrors one of Earth's most biologically productive environments. Circulation patterns in the ocean remain uncertain, but likely involve convection driven by temperature differences. Warm water rises from hydrothermal vents at the ocean floor, cooling as it reaches the ice ceiling, then sinking back toward the bottom, creating convection cells that mix the ocean over time. Tidal forces from Saturn may generate additional currents, flexing the ocean and creating turbulence. This mixing is crucial for habitability. It distributes nutrients, disperses metabolic wastes, and prevents stagnation. The ocean isn't static. It flows, circulates, mixes. And this circulation transports whatever chemistry happens at the seafloor throughout the entire ocean volume, spreading molecules, distributing energy, potentially distributing life if life exists. The ocean is dynamic, not a frozen-in-time isolated reservoir, but an active hydrologic system responding to tidal forcing, thermal gradients, and chemical reactions at the rock-water interface. The ocean has existed for an estimated 1 billion years, sufficient time for chemical evolution and potentially biological evolution. A 2019 study suggested that Enceladus's ocean formed relatively recently in solar system history, possibly within the last billion years, though earlier formation remains possible. Either way, a billion years provides enormous opportunities for chemistry to explore complexity, for molecules to organize, for systems to evolve. On Earth, life appeared within a few 100 million years of liquid water's persistence. Did similar processes occur on Enceladus? We don't know, but we know the ocean exists. We know it's warm. We know it has the right chemistry. We know it's been stable for vast spans of time. And we know it's connected to hydrothermal vents where on Earth life thrives. Every characteristic we associate with habitability exists in Enceladus's ocean. A stage is set. The question remains, did the play begin? Now we arrive at perhaps the most exciting aspect of Enceladus, what the plumes contain. Cassini's instruments, particularly the ion and neutral mass spectrometer and the cosmic dust analyzer, sampled plume composition during those 22 close flybys, analyzing both the gas phase and the ice grain composition. What they found reads like a shopping list for life, water, essential elements, energy sources, and complex organic molecules. Let's go through the inventory systematically, because each component tells part of the story. Water dominates. Over 90% of the plume consists of H2O as vapor and ice grains. But it's the remaining 10% that makes astrobiologists' hearts race. Carbon dioxide reaches several percent, providing carbon for organic chemistry. Methane appears in quantities exceeding abiotic production estimates. Molecular nitrogen contributes to the 28 Dalton signal. Ammonia reaches approximately 0.5%, acting as antifreeze and providing nitrogen. The fundamental building blocks are present. Early detections identified simple organic compounds, formaldehyde, acetylene, propane molecules below 50 atomic mass units. Interesting, but not extraordinary. Then, in 2018, Frank Postberg's team announced something remarkable: macromolecular organic compounds with masses exceeding 200 atomic mass units, some reaching 1,000 to 2,000 AMU. These aren't simple molecules. These are complex carbon structures with multiple rings and chains, bearing oxygen and nitrogen atoms, showing unsaturated bonds indicating chemical reactivity. The molecules suggest a thin, organic-rich film floating atop the ocean water surface, concentrated organics produced by ocean chemistry then ejected in the plumes. On Earth, similar films form at the air-sea interface. On Enceladus, this film samples the ocean's organic inventory. And what an inventory it is, complex enough to bridge the gap between simple chemicals and the molecules life requires. Complex enough to make you wonder what else might be happening in those ocean depths. But the discoveries continued, accelerated. The 2018 analysis revealed aromatic organic compounds, benzene rings, and polycyclic aromatic hydrocarbons. Peak signatures at 77 to 79 atomic mass units indicated phenyl and benzene cations. The 91 AMU peak revealed tryptophan ions. These aromatic compounds form the backbone of more complex organic chemistry, serving as essential precursors to amino acids and nucleobases. On Earth, PAHs are everywhere in combustion products, in meteorites, in the interstellar medium. But finding them erupting from an icy moon's ocean? That suggests active organic synthesis occurring in liquid water in contact with minerals at elevated temperatures. The chemistry happening in Enceladus's ocean isn't simple dissolution and dilution. It's synthesis. It's building complexity from simpler components driven by energy and catalyzed by minerals. It's exactly the kind of chemistry that could lead to life. Then came the January 2025 breakthrough. Nozer Khawaja and colleagues reanalyzed data from the October 9, 2008 flyby, a pass conducted at extremely high velocity of 17.7 kilometers per second. The high-speed impact fragmented molecules differently than slower encounters, revealing chemistry hidden in previous analyses. The results stunned the scientific community. Aliphatic compounds, straight-chain hydrocarbons of various lengths, esters and ethers, oxygen-bearing organics indicating oxidation chemistry, cyclic compounds including heterocyclic structures with nitrogen and oxygen in rings, nitrogen, oxygen-bearing compounds suggesting nitrogen fixation, and amines, organic molecules with nitrogen fixation, and amines, organic molecules with nitrogen bonds. This wasn't just complex chemistry. This was chemistry, one step away from biochemistry. The molecules detected are exactly the types that biological systems use and synthesize. Are they biological in origin? Don't know. But they're consistent with what active biology would produce. On April 13, 2017, Hunter Waite announced perhaps the most significant discovery of all, molecular hydrogen. Cassini's October 28, 2015 flyby at 49 kilometers, altitude detected H2 gas at approximately 1% of plume composition. This discovery's implications cascade through astrobiology. Molecular hydrogen on Earth forms primarily through serpentinization, chemical reactions between water and rock minerals like olivine and pyroxene at elevated temperatures above 90 Celsius. The reactions produce serpentine minerals, hydrogen gas, and heat. Finding hydrogen in the plumes proves that Enceladus's ocean floor hosts active hydrothermal chemistry. Water is reacting with rock right now, at this moment, deep beneath the ice. More importantly, the hydrogen provides a chemical energy source for potential life. On Earth, methanogenic microbes metabolize hydrogen for energy, combining it with carbon dioxide to produce methane and water. The presence of excess methane in Enceladus's plumes, more than expected from abiotic processes, could indicate ongoing serpentinization or tantalizingly biological methanogenesis. The final piece of the habitability puzzle arrived. June 14, 2023, phosphorus. Frank Postberg's team analyzed ice grains from Saturn's E-ring traced to Enceladus and found sodium phosphates, orthophosphates, specifically PO4 triple minus and HPO4 double minus. 9 grains out of 345 analyzed showed clear phosphate signatures. Concentration estimates suggested at least 100-fold higher phosphorus levels than Earth's oceans, potentially 500 to 1,000 times higher. This discovery completed the Schnapps requirements: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, all 6 essential elements now confirmed in Enceladus's ocean. Phosphorus, essential for DNA, RNA, ATP cellular energy, and cell membranes, represents what scientists call the strictest requirement of habitability. The high concentration shocked researchers, as phosphorus usually remains locked in minerals. But Enceladus's carbonate-rich alkaline ocean dissolves phosphates from carbonaceous chondritic rock far more efficiently than expected. Every element life needs, present. Every condition life requires, met. The only question remaining, is life actually there? Silica nanoparticles provided additional evidence for hydrothermal vents. Detected in March 2015, these particles, just 2 to 8 nanometers in diameter, nearly pure silicon dioxide, can only form where liquid water and rock interact at temperatures exceeding 90 Celsius, potentially above 150 Celsius. The formation mechanism proceeds as follows. Hot water circulating through Enceladus's porous rocky core leaches silica, creating supersaturated solution. As this silica-rich hot water rises toward the ocean floor and enters the cooler bulk ocean, rapid temperature decrease causes explosive crystallization of nanoparticles. The narrow size range reflects specific supersaturation and temperature conditions at Enceladus's hydrothermal vents. Combined with hydrogen detection, silica nanoparticles provide compelling evidence for active hydrothermal systems analogous to Earth's seafloor vents. Enceladus hosts lost city-type environments where on Earth life thrives. Chemical disequilibrium between hydrogen and methane offers thermodynamic gradients that life could exploit. Every characteristic of Earth's chemosynthetic ecosystems exists on Enceladus. We found an alien lost city. Rosalie Lopez articulated the significance. You have everything you need to form life. Scientists now actively search for biosignatures in existing Cassini data and plan future missions. Target biosignatures include amino acids with specific chirality indicating biological rather than abiotic synthesis, lipids suggesting cell membranes, fatty acids with characteristic chain lengths, nucleotides, and isotopic ratios showing biological processing. Cassini wasn't designed for life detection. Its instruments lacked the sensitivity and specificity to definitively identify biosignatures. But future dedicated missions could answer the question definitively. A Plume sampling mission equipped with proper life detection instruments could fly through the geysers, collect ice grains, analyze them in situ, and either detect life or set strict upper limits on its abundance. The technology exists. The target is known. The question awaits an answer. Will we find life on Enceladus? We've explored two profoundly different worlds now, and it's worth stepping back to appreciate just how different they are. Titan, massive, distant from Saturn, cloaked in a thick nitrogen atmosphere, its surface adorned with methane seas and organic dunes, hiding a deep water ocean 55 to 80 kilometers beneath the surface. Enceladus, tiny, close to Saturn, airless, erupting continuous geysers from a warm, salty ocean just kilometers beneath the South Polar ice. One operates through atmospheric chemistry at frigid temperatures. The other operates through aqueous chemistry at hydrothermal vent temperatures. One builds complexity in the atmosphere and lets it fall. The other builds complexity in the ocean and erupts it to space. Yet both are ocean worlds. Both have the ingredients for life. Both challenge our preconceptions about habitability. How did two moons orbiting the same planet evolve so differently? The answer reveals fundamental principles about how worlds were. Size determined much of their divergent fates. Titan's large mass, over 1,000 times greater than Enceladus, meant several things. First, sufficient gravity to retain an atmosphere despite temperatures where gases should escape. Second, larger internal heat reservoir from radioactive decay, providing sustained geological activity. Third, slower cooling, meaning interior heat persists longer. Titan could build and maintain an atmosphere, drive a methane cycle, and support internal liquid over billions of years, essentially through its own mass. Enceladus lacked these advantages. Too small to retain atmosphere, too small to generate substantial radiogenic heat, too small to stay warm on its own. Without tidal heating from orbital resonance with Dione, Enceladus would have frozen solid eons ago and remained geologically dead. But that resonance changed everything, transforming a moon that should be a frozen wasteland into one of the solar system's most active bodies. Sometimes size matters. Sometimes orbital mechanics matters more. Their orbital architectures created divergent thermal regimes. Titan orbits at 1.22 million kilometers, taking 16 days per orbit, experiencing minimal tidal forces. Its eccentricity of 0.0288 generates some tidal heating but far less than necessary to explain observed activity. Titan's heat budget comes primarily from residual accretional heat and radioactive decay, supplemented by minor tidal contributions. This moderate heating maintains the subsurface ocean but doesn't drive dramatic surface activity. Enceladus orbits at just 238,000 kilometers, 5 times closer, experiencing far stronger tidal forces. Its 2001 resonance with Dione maintains orbital eccentricity despite tidal damping. Every 33 hours, Enceladus experiences enormous tidal squeezing and stretching, generating up to 50 gigawatts of heat, 200 times its radiogenic heat production. This tidal furnace powers everything: the ocean, the hydrothermal vents, the geysers, the geological activity. Enceladus is a tidal world. Its very existence depends on gravitational resonance with Dione and proximity to Saturn. Without that specific orbital configuration, Enceladus wouldn't exist as we know it. From Saturn's perspective, the two moons present vastly different views. Titan appears enormous from Saturn's cloud tops, spanning about 17 degrees, larger than the Moon from Earth, glowing orange through its thick atmosphere. But Titan is distant, removed, independent. Enceladus appears tiny from Saturn, less than 0.5 degrees, but it's intimately connected. Enceladus feeds Saturn's E-ring with continuous particle injection. The ring extends from Mimas's orbit past Titan, but it's thickest at Enceladus's orbital distance. Approximately 200 kilograms per second of material ejected from Enceladus, about 70% escapes to populate the broader system, while 30% remains in the immediate ring. Saturn and Enceladus exchange material constantly. Enceladus exhales ice. Saturn's magnetosphere bombards it with particles. Some ejected material spirals into Saturn's atmosphere. They're coupled, connected, interactive. Titan operates more independently, protected by its thick atmosphere from direct magnetospheric interactions. The nature of their oceans differs profoundly. Titan's ocean lies 55 to 80 kilometers deep beneath solid ice, reaching 250 kilometers in depth, trapped between the ice shell above and high-pressure ice below. It's inaccessible, isolated, difficult to sample. Chemistry occurs in darkness, at cold temperatures, with limited nutrient exchange between ocean and rocky core. The April 2025 study suggested minimal biomass potential, perhaps only pounds of cells if life exists, due to nutrient limitations. Yet the ocean persists, enormous in volume, stable for billions of years. Enceladus's ocean lies just 1 to 5 kilometers beneath the south polar surface, 10 kilometers deep, directly connected to a porous rocky core where hydrothermal vents operate. It's accessible through the tiger stripes, actively venting to space. Chemistry occurs at elevated temperatures reaching 90 to 80 Celsius at vent sites. Nutrients circulate from rock to water to plumes. The ocean is dynamic, energetic, connected. If you wanted to design an ocean for life, you'd design something like Enceladus's ocean. Yet despite their differences, both worlds expand our understanding of habitability. Titan demonstrates that prebiotic chemistry can proceed at temperatures where water is solid as rock, operating through methane instead. It shows that complex organic synthesis doesn't require life, that atmospheric photochemistry alone can build molecules of extraordinary complexity. It proves that multiple habitable environments can coexist on one world. Methane-based surface chemistry and water-based ocean chemistry, potentially hosting two independent origins of life. Enceladus demonstrates that tiny worlds can remain geologically active for billions of years given the right orbital configuration. It shows that subsurface oceans need not be inaccessible, that some ocean worlds conveniently sample their interiors for us. It proves that all the ingredients for life can assemble in alien environments under ice on small moons far from the sun. Together, they teach us that habitability is diverse, that life's requirements can be met in myriad ways, that we should expect ocean worlds throughout the galaxy harboring conditions suitable for biology. Alan Stern has argued that ocean worlds might be 100 to 1,000 times more numerous than surface ocean planets like Earth throughout the galaxy. If true, and evidence from our solar system suggests it might be, then the most common habitable environments in the universe aren't Earth-like worlds basking in stellar habitable zones. They're ice-covered ocean moons and planets warmed by tidal forces or residual heat, existing anywhere in any stellar system regardless of distance from the star. Life in the universe might predominantly exist beneath ice, in darkness, powered by geochemistry rather than photosynthesis. Titan and Enceladus are templates for countless billions of similar worlds scattered through the Milky Way and beyond. What we learn about habitability here, in Saturn's system, applies everywhere. These aren't just two interesting moons. They're windows into the most common class of habitable environments in the cosmos. And we're just beginning to understand what that means. The discoveries made by Cassini. Huygens weren't endpoints. They were beginnings. Every answer raised new questions. Every measurement suggested new investigations. Titan and Enceladus have transformed from curiosities into priorities, prime targets for dedicated missions that will return in the coming decades. NASA's Dragonfly mission leads the way, a 450-kilogram octocopter that will fly across Titan's surface beginning in 2034, sampling organic chemistry at multiple sites, searching for biosignatures at Selk crater where water once mixed with organics during impact melting. The $335 billion investment reflects Titan's significance. 8 rotors will carry the craft up to 16 kilometers per flight, hopping between landing sites, analyzing surface composition with a mass spectrometer, detecting seismic waves from methane seas, capturing microscopic and panoramic images. It's a revolutionary mission architecture. The first aircraft on another moon, the first dedicated astrobiology mission to the outer solar system. Are you ready to see what Dragonfly discovers? Dragonfly will first explore the Shangri-La dune fields near Titan's equator, vast expanses of organic sand covering millions of square kilometers. The craft will hop between landing sites sampling different materials, dark dunes rich in complex organics, into dune areas with coarser material, possibly including water ice exposed in crater walls. Then comes the major transit to Selk crater 90 kilometers in diameter, where the 80-million-year-old impact created transient pools of liquid water that interacted with surrounding organics before refreezing. Selk's floor preserves pristine samples of this chemistry, organics manufactured in the atmosphere mixed with impact, melted ice subjected to heat and pressure, allowed to react in liquid water, then frozen and preserved undisturbed. If anywhere on Titan offers clear evidence of prebiotic chemistry advancing toward biochemistry, it's Selk. Dragonflies. Its seismometer will detect waves on distant methane seas. Its cameras will document alien landscapes. Starting in 2034, we'll see Titan through Dragonfly's eyes. What will we discover? For Enceladus, mission concepts proliferate, each more ambitious than the last. The proposed Enceladus. LifeFinder would conduct multiple close flybys through the Plumes with instruments specifically designed for life detection. Unlike Cassini's general-purpose instruments, ELF would carry amino acid analyzers checking for chirality. Biological molecules show handedness that abiotic chemistry doesn't produce. It would detect lipids indicating cell membranes, analyze fatty acid chain lengths characteristic of biology, search for nucleotides, and measure isotopic ratios showing biological fractionation. ELF could definitively detect biosignatures if they exist in concentrations above its detection thresholds. An Enceladus orbiter concept would go further, settling into orbit around the tiny moon, characterizing geology and plume activity over an extended mission, mapping gravitational and magnetic fields, tracking seasonal variations in eruption intensity. Most ambitious of all, sample return. A spacecraft could fly through the plumes, capture pristine ice grains in aerogel collectors, seal them in a sterile return capsule, and bring them to Earth where laboratory analysis could detect biosignatures at concentrations and specificities impossible with spacecraft instruments. Europa remains a parallel priority. NASA's Europa Clipper, launched in October 2024, will arrive at Jupiter in 2030 and conduct 49 close flybys investigating Europa's ice shelf thickness, ocean characteristics, surface composition, and plume activity. Yes, Europa has plumes too, though far less active than Enceladus's. ESA's JICE mission, the Jupiter Icy Moons Explorer, will study Ganymede, Callisto, and Europa. These missions will determine whether Europa's ocean harbors similar chemistry to Enceladus's, whether it hosts hydrothermal vents, whether its surface shows evidence of recent ocean exposure. Europa's ocean is larger and potentially older than Enceladus's, making it equally promising for astrobiology. Between Europa and Enceladus, we'll sample 2 independent ocean world environments, testing whether the habitability we've inferred translates into actual habitat, whether chemistry becomes biology. These aren't abstract questions. Within the next 2 decades, we'll have concrete answers. The search for life beyond Earth has entered its decisive phase. What will we find? 3 possibilities exist, each with profound implications. First, we detect clear biosignatures, amino acids with biological chirality, lipids and cell membrane configurations, isotopic ratios indicating biological processing, perhaps even intact cells or cell-like structures. This would prove life arose at least twice in our solar system, suggesting it's common throughout the universe. Second, we detect ambiguous results, organic complexity that could be biological or abiotic, requiring sample return and laboratory analysis for definitive determination. This would torture us with uncertainty, but drive even more ambitious missions. Third, we detect no biosignatures despite thorough investigation, setting upper limits on life's abundance if it exists. This wouldn't prove sterility. Life might exist in concentrations below detection, in locations we haven't sampled, or in forms we don't recognize, but it would temper expectations. Personally, I believe we'll find life. The ingredients are there, the conditions are right, the energy is available, the time has been sufficient. Nature tends toward complexity when conditions permit. But I could be wrong. That's why we explore. The broader lesson extends beyond individual worlds. We've learned that habitability is diverse, that life's requirements can be met in ways we didn't anticipate, that ocean worlds represent a major class of potentially inhabited environments. We've learned that size doesn't determine geological activity. Orbital mechanics matters more. We've learned that atmospheres aren't necessary for habitability, that subsurface oceans might be more stable and protected than surface oceans. We've learned that organic chemistry proceeds at temperatures ranging from -179 Celsius to +180 Celsius, that prebiotic synthesis doesn't require specific narrow conditions, that complexity emerges readily when energy and materials are available. Every discovery expands the domain of habitability. Every measurement increases the probability that we share the universe with other life. Titan and Enceladus have been our teachers, showing us that the cosmos is far more hospitable than we imagined. How many other ocean worlds orbit distant stars, harboring their own seas, their own chemistry, perhaps their own biologies? We're learning to recognize them, to characterize them, to eventually visit them. As we prepare to leave Saturn's system and return to Earth, take one last look at these 2 extraordinary worlds. Titan, shrouded in orange haze, cycling methane through atmosphere and lakes, building organic complexity grain by grain, hiding a deep ocean beneath kilometers of ice, a world operating on alien chemistry yet following familiar physical principles. Enceladus, brilliant and white, erupting continuous geysers from tiger stripe fractures, sampling its warm, salty ocean for us, providing direct access to one of the most promising habitable environments beyond Earth. A tiny moon that shouldn't be active but defies expectations through the power of orbital resonance. Both moons have transformed our understanding of where and how life might exist. Both have shown us that the universe is far stranger, far more diverse, far more potentially alive than we imagined. And both remind us that the search for life beyond Earth isn't speculation or science fiction. It's ongoing science, driven by evidence, guided by measurements, leading toward answers within our lifetimes. The age of ocean world exploration has begun. Will we find that we're alone? Or will these frozen moons reveal that life, like water and chemistry and energy, is a common feature of the cosmos? Our journey through Saturn's ocean worlds is complete, but the real exploration is just beginning. In 2028, Dragonfly will launch toward Titan. In 2030, Europa Clipper will begin its investigation of Jupiter's ocean moon. Future missions will return to Enceladus, sampling its plumes with instruments designed to detect life. Within your lifetime, we may answer one of humanity's oldest questions. Are we alone? These frozen worlds at the edge of the solar system, places of methane rain and ice geysers, of organic chemistry and hydrothermal vents, might harbor the second genesis of life in our solar system. If they do, it will prove that life is not rare, not special, not limited to Earth. It will mean we live in a living universe, populated by countless ocean worlds beneath ice shells around distant stars. What does it mean to you, knowing that life might exist on these alien seas? What does it change about how we see our place in the cosmos? Perhaps the greatest lesson from Titan and Enceladus is this: look beyond the obvious. The most habitable places aren't always the most Earth-like. Sometimes, the most promising locations for life are the least expected. Tiny moons we barely noticed until recently, worlds that seem hostile but harbor secret seas, places where chemistry proceeds in darkness and life might bloom without sunlight. The universe is full of surprises. We're learning to recognize them. Thank you for joining me on this voyage. Until our next journey, keep looking up at the stars. And remember, somewhere out there, 1.2 billion kilometers away, water is erupting from an ice moon's surface, carrying with it perhaps the answer to everything.